I'm working on developing a game in Godot, but my character has a problem. Well, he has many problems. For starters, he's a pill shape. But there's an even more important issue right now. He's not able to walk up a staircase. This might not seem like too big of an issue, but I have a history of stairs. Lots of games replace staircases with ramps to get around this problem. This will mostly work, but there will always be some edge cases where there is a step or jump in the terrain. This could be something simple like a rock in the ground that causes a sudden jump in height. It would be odd for the player model to get stuck on such a small object. Additionally, physics objects should interact with the stairs as though they are flat. For example, a ball should not roll down the staircase like it's a ramp. So, for this scenario, a level designer would need to make a separate set of meshes for every staircase so the player can travel smoothly across them like a ramp, but physics objects interact with the visual shape. Since the steps that a player can encounter in an environment will vary significantly, I need to make sure that the player will be able to climb any set of stairs. Each steps could have a different height, depth, or slope. Creating these steps could be achieved by a few different methodologies. So, for the rest of this video, I'll be diving into how to generate staircases in Godot. Whenever I work on a project, I often run into scope creep, so this video will just focus on creating these staircases for the player character. I'll focus on methods for having the player climb staircases in a future video. For this video, my goal is to generate various types of staircases for the player to climb. Whatever methodology I end up using will need to have a few requirements. It must create various staircases with different step heights and depths as identified earlier, be easy to create lots of staircases so that I can test the player on all of them, and be adjustable in case a new scenario comes up in the future. There are many ways to create staircases in the game engine. However, let's just consider a few to limit the project scope. The simplest method would be to just stack primitive box shapes on top of each other in the game engine. Another natural option would be to create a staircase in a third-party software such as Blender and import it into the game engine. The last and most complex option would be to procedurally generate the mesh directly in the game engine. Let's evaluate each of these methodologies against the requirements identified earlier. The solution needs to support configurable step height and depth, scalable to generate lots of staircases, and adjustable for future scenarios. The first option to simply stack boxes in the game engine is very simple. It would take some effort to manually adjust the different step heights and depths, but it could be done. Since it requires a lot of manual work, it's not very scalable to create many staircases. As for adjustable, it would require many manual steps to adjust the existing staircase to meet a new set of parameters, as each box step would need to be modified manually. The second option is to make the staircase in a third-party software like Blender. Making the mesh in Blender is simple and could be achieved using some manual work or modifiers. This is easy to adjust for various parameters if using a modifier. However, it's not very scalable, as exporting the mesh as an FBX and then importing it to Godot and configuring the mesh requires a bit of manual work. The third option, and most complicated, is to manually generate the mesh in the game engine. This would be configurable since the mesh is created in the engine. As for scalability, the node can easily be duplicated and modified for new parameters, and it would be adjustable as the staircase could be modified by adjusting the configuration values. Looking at the results for each method, it seems like procedural mesh generation is the best option as it checks all the boxes. However, it does require the most upfront work to implement. How hard could procedural mesh generation really be? Procedural mesh generation is like making the mesh in Blender, but instead of modifying the mesh by hand, I'm going to write some instructions for the computer to follow so it knows what to do. I've been using the term mesh many times. I'll start by defining what a mesh is. A mesh is how your computer shows a virtual object. A mesh is a collection of vertices, edges, and faces. Also, since computers aren't the best at complex instructions, all the faces in the mesh are usually triangles. This is because a triangle can only face one direction with no curves or bendings like a square or other polygon could have. Software like Blender can show non-triangle faces, but game engines like Godot only work with triangles as they need to be very optimized. In Godot, the Mesh Instance 3D node can take a mesh and render it in the scene. The Mesh Instance 3D node can be added to a child of the staircase node. Additionally, since the character needs to be able to walk up the staircase, it will also need a shape in the physics environment. This can be achieved by creating a physics body 3D node with a child collision shape 3D node. The physics body 3D node defines how the object acts within the world. Is the object static or dynamic? What material properties are associated with it? And so on. The child collision shape 3D object defines the shape of the staircase. The mesh instance 3D and collision shape 3D can be given the staircase mesh as a parameter. In Unity, the equivalent would be to add a mesh renderer and mesh collider components to an object. A rigid body component would be needed if the game object needs specific properties as well, but is optional if the staircase is static. All that is left now is to create a mesh to provide as parameters for the nodes. The most complex part. Before I try to create the whole mesh at once, it's good to start off simple. The simplest mesh that can be created would be a triangle. Using the surface tool object in Godot, I can provide a set of vertices and some configuration properties to define a triangle. The surface tool has multiple configurations. The simplest is mesh.primitiveTriangles. This allows for adding 3 vertices as a triangle via the addVertex method. Calling this with 3 coordinates would create a triangle with some vertex on each of the provided coordinates. Once all the vertices have been added, the commit method can be invoked to get the generated mesh object. This mesh can then be provided to the mesh instance 3D node to render it on the screen. It may look a bit weird with the light source. This is because no normal vectors have been provided. The normal vectors define which way the face is pointing and is used to determine how light interacts with the object. Surface Tool has a method named generateNormals to automatically populate the normal vectors for each vertex and face. A square or plane shape can be created by adding a second triangle which shares 2 of the vertices with the previous triangle. This can then be further extended to create a cube by adding 6 faces along each plane. Just following these steps may lead to some issues and unexpected holes in the mesh. This is due to backface culling optimization. Backface culling is the process of skipping rendering any triangles that are pointing away from the camera. This is useful since most meshes define a contiguous surface that won't have any holes. You can't see inside a solid object, so there is no reason to render parts of the object that are pointing away from the camera. Sorry to any topology experts if I'm butchering this definition. A simple example of this would be a cube. Only 3 faces can be pointed towards the camera at any given time, so the faces pointing away from the camera can be skipped as they are covered by the 3 faces pointing towards the camera. But this begs the question, how does the camera know if a face is pointing toward the camera? And why are there still some arbitrary holes in the mesh? The computer knows if the face is pointing towards the camera by checking if the vertices are defined in a clockwise order. Let's look at an example to understand more. Start off by defining a triangle with vertices 1, 2, 3, where 1 is at the top, 2 is at the bottom right, and 3 is at the bottom left. When looking at the triangle from the front, if the vertices are defined in ascending order, 1, then 2, then 3, then the face should be drawn. These vertices are ordered in clockwise fashion starting from the top, then to the bottom right, then the bottom left. Flipping the triangle to face away from the camera would cause the vertices to now be ordered 1, 3, 2. The vertices are now ordered in a counterclockwise fashion starting from the top. No matter the orientation of the triangle in 3D space, the vertices will always be in clockwise order when pointing towards the camera, and counterclockwise order when pointing away from the camera. If backface culling is enabled, then the computer knows to skip drawing the triangle if it's facing away, because there should be another triangle in front of this face pointing towards the camera. In our cube example, this is true as there is always one face pointing outwards along each axis. The faces pointing away from the camera will be covered by the 3 faces pointing towards the camera. Backface culling can be disabled for some applications. For example, the bush in Fortnite is made up of a few leaf textures along different planes. This object doesn't have any volume or shape, and would normally have the backface culling disabled so each leaf texture is visible from all angles, even when facing away from the camera. Now I have a script to generate a cube at will. However, there is still some work left to get to a staircase. Just like with the cube, defined as 6 faces, the staircase needs to be defined programmatically as well. I've decided to define each step as a vertical box. The first step has a front face starting at the ground, a top face attached to the top edge of the front face, and 2 sides to cap off the edges. The subsequent step in the staircase will have a front face starting from where the first step's top face ends. A top face then attached to the top edge of this new front face, and two side faces that reach all the way down to the ground. This allows for the staircase to have solid edges. Then, this pattern continues up until the last step, but with an added back face that is attached to the back of the top face, and stretches all the way down to the ground. I wrote a helper function in my script to make creating a square from 4 provided vertices. Using a for loop, I can loop through each step following the instructions laid out earlier for the front face, top face, and side faces. The front and top faces are moved up and back with each step. The side faces get taller with each step to continue to reach all the way down to the ground. For each step, I can identify the bottom, top, front, and left bounds before creating the faces. Each step has the same width, so the left and right parameters can remain the same. Then, use these save values to generate the various faces. There are some parameters for the entire staircase that need to be provided as user input. Specifically, the height of each step and the depth of each step. These values can be used to define how far back from step depth and up from step height each subsequent step needs to be moved. These values can be plugged into our for loop from earlier to allow for configuring how the staircase looks, as well as the number of steps to include in the staircase. The for loop looks a bit complicated when including all these steps, but each section of code can be seen as adding one of the faces specified earlier and how I define each step as a vertical box. This script can be labeled as a tool in Godot. Tools allow for modifications made in the editor to be applied directly to the node in the scene in real time. Adding a script property with the export decorator allows for the property to be seen in the Godot editor. The for loop specified earlier is a part of the helper function, which is invoked anytime a parameter is changed. I have overwritten the get and set operators for each parameter of the node so that when they are modified in the editor, they will update the stair mesh to match. Each time one of these parameters is modified, a new mesh is generated with new properties and attached to the Mesh Instance 3D and Collider Shape 3D child nodes of the Staircase node. Now that the staircase will update whenever these properties are changed, I can make a set of staircases to test the player character against. It is good to add some steps that vary in height and depth to check all the behavior. Maybe some that are too narrow for the player to climb easily, as well as some that are too tall for the player to step up. Also, since the values are updated in real time, it allows for some fun interactions in the editor where the shape can stretch out in each direction. You may have noticed that there is a square texture on the side of the staircase, and this texture stays the same size as the staircase is stretched. This is because I have set the UV coordinates for each vertex to match their position in the world space, like a triplanar mapping projection. Faces on the top face use their coordinates in the horizontal plane to sample the reference texture. The front face uses coordinates in the front-back vertical plane, and the side faces use their coordinates in the left-right vertical plane to sample from the reference texture. UV mapping is an important concept to ensure that textures are applied to meshes properly, and 3D modeling software like Blender have lots of tools to unwrap a mesh into the UV plane for a specific texture map. Although all this is a bit out of scope for covering in this project. You can look at the reference code if you're interested to learn more on your own. I can now create various staircases for the player to interact with. Earlier I mentioned that the staircase script will provide a mesh to the Collision Shape 3D node as well. This will allow the staircase to interact with the physics engine and other objects in the scene. If I were to throw some virtual spheres at it, it would bounce or roll off the sides. If the player walks into the object, they will interact with each step. However, the collision shape for the staircase doesn't need to necessarily be the same as the visual shape. For example, if I had a complex railing model along the side of the staircase, it might be easier to treat the railing as one large square instead of adding each post as its own physics object. Simplifying the collision shape can lead to more predictable interactions with the physics object as well as better performance. However, the staircase is a pretty simple mesh as it stands right now. I could add an option to treat it as a convex mesh, turning each step into a ramp that allows the player to slide up. This method won't work for curved staircases, but for straight staircases, treating it as a convex shape will allow for a smooth ramp for the player to character to slide up. Although it will lead to some odd interactions of physics objects rolling up and down instead of stopping on each step. The Unity game engine has a plugin called Pro Builder that has similar script for generating staircases in the engine as well as other primitive shapes. This is quite useful for level designers as they can quickly create various shapes for the player to interact with. As I mentioned earlier, this can also be used to create collision shapes for objects in the scene as well. Many objects in the scene may have complex meshes but only require a simple shape for collision. The ability to quickly create various primitive shapes and objects such as staircases allows for quite a bit of freedom in level design. Now that I'm able to generate staircases of various sizes and shapes, I can test the character's interactions to make them smoother. The default character controller script in Godot does not support snapping up staircases and will sometimes get stuck when one walking into a specific step. As of now, I have implemented a snapping algorithm to have the player essentially teleport and slide up a step when they run into it. This is useful to allow for the character controller to move up and down steps with a certain set of bounds. However, this does lead to some jittery movement when walking up many steps quickly. This leaves some room for improvement, and I'm looking into adding a floating character controller for an even smoother transition up and down steps. But that will be for a future video. Thanks for making it all the way to the end of the video. Procedural mesh generation isn't required to create stairs, but it opens the door to a lot of other abilities that wouldn't otherwise be possible, such as terrain generation, dynamically modified meshes, and a lot of other possible features. Starting with something that is simple but with clear parameters, such as a staircase, is a good place to explore the subject. Slightly more complex than just a plane, but easier to understand than something like jumping straight into terrain generation. I wrote up a text summary for how the stair generation script works on my website. You can find the link in the description if you're interested in a text-based explanation that is significantly shorter than this long-form video content. It's been a bit since my last video, very busy with work and a lot of big life events last year that delayed any video creation. The Godot OpenKCC project has gotten along quite well so far. Many areas to explore from GD extensions, automated documentation and website generation, and simply the physics logic translated to GD script and C# for the Godot game engine. I'll do my best to include all these topics in future videos. It might take some time for me to acclimate to the new environment. Make sure to subscribe if you're interested in learning more about these topics in my future videos. And, as always, have a great day.